Okay, I think we have to keep a schedule and just start. Please take seats. Good evening. I have a privilege to chair the last plenary session of this nice conference. My name is Emil Zolotayavka. I'm professor of material science and engineering at Technion in Haifa. And I would like to introduce our distinguished guest, Professor Seeram Ramakrishna from Singapore, which is giving class lecture in this symposium. Professor Ramakrishna is currently the Vice President for Research Strategy and Professor of Mechanical Engineering at the National University of Singapore. Before this, he served as the Dean of Faculty of Engineering during 2003 and 2008. He is also the founder and co-director of Nanoscience and Nanotechnology Initiative in the same National University of Singapore since 2002. Professor Ramakrishna is a well-known expert in materials engineering. He is a fellow of major professional societies in Singapore, ASEAN, UK, and USA. He is a recipient of Cheng Chang Professorship of China, ASEAN Outstanding Engineering Award, News Outstanding Researcher Award, Lee Kuan Jeff Fellowship, and Cambridge Narrow Scholarship. Today, Professor Ramakrishna will speak about the quest for clean energy, water, and regenerative medicine using nature building blocks. Please, Professor Ramakrishna, the podium is yours. 40 minutes.
Thank you, Chairman, and good afternoon to all of you. I realize this is going to be a challenge for you. This being a last lecture, I'm sure keeping the great attention would be a challenge. It is also equally a challenge for me because it's almost midnight in Singapore. So I'm trying myself to be awake and give you a nice lecture and wrap up this as the last lecture for this wonderful conference put together by Noam as well as his colleagues. My goal today is to take you through some of the exciting work we are doing at the National University of Singapore. But we're not the only one doing this kind of research. You would find there are many groups around the world pursuing similar directions. So it is my pleasure to introduce you, those who are not familiar with this area of research. Those who are already familiar, perhaps this is just an addition to what you already know. And basically I intend to focus, we have a platform concept and how that is useful in terms of harvesting solar energy, in treatment of the water, as well as dealing with regenerative medicine. I want to start with this particular slide because there's only one reason I wrote the book. The Changing Face of Innovation, is it shifting to Asia? And it's coming out next month, so I thought I'll take this as a free advertisement and I tell you. But what is more interesting is give you those numbers. These are the global R&D expenditure according to the Battelle report, one of the very well-recognized R&D magazine called Battelle. They actually manage a large R&D organization in the United States. According to them, the number of amount of research dollars that are committed around the world looks like that. And I think with the years ahead, these numbers are likely to grow. That gives an idea how the innovation is shaping up in years to come. My outline is to basically demonstrate that the natural building blocks, which are basically high aspect ratio fibers, does have a role in terms of helping out solving some of the interesting issues we face today. I would start with the population growth obviously this is one of the serious concerns. And perhaps we are the generation witnessing a doubling of the population in our lifetime. And if you notice which are the regions that are growing, obviously India, China, Africa are substantially growing, and of course other parts of the world as well. There is a certain degree of growth. Because of this growth, as well as the high degree of consumption of the water as well as other resources, there's clearly going to be a shortage of water. And in fact, yesterday's news, they said more than 1 billion people did not have a good access to the drinkable water. And in years to come, next 30, 40 years, that's going to be almost half the world population would be water stressed. And the second one is energy, again, which is also a theme of this particular conference. You notice that these developing countries with a huge population base, they are beginning to have a better quality of life, and they're going to actually absorb a lot more energy, and eventually they would settle somewhere here in terms of the per capita energy consumption. Despite all the calls for global warming, my guess is they would still continue to use large quantities of energy. And here is an interesting scenario for you. This is a 1973 global energy mix, that is 2007 global energy mix. If you notice, almost 80% of the primary energy demand of the world is met through the fossil fuels, which are basically oil, gas, and coal. And the renewables comprise about 18%. That's about the total global composition, or the energy mix. Now, fast forward another 20 years. Is this going to change? Probably not, especially after watching what is going on at Copenhagen discussions. One scenario, the energy consumption is going to grow up totally, but in terms of the total energy mix itself, it is unlikely to change significantly unless those people at the politicians as well as the policy makers at Copenhagen Summit decide to go that way. That is, they would have a much higher proportion of renewable energy as contributing to the primary energy needs of each country. So essentially, in a most optimistic scenario, you could have a total energy mix of the world contributed by up to 40% from the renewable energy sources. That's likely. Then, of course, you will see a lot more nuclear, hydro, as well as solar energy, wind, biomass, all those things. And nuclear is particularly coming up very strongly in Asia. Right now, close to 70% of the world's new nuclear reactors are being built in Asia. That amounts to about 60 new nuclear reactors that would be coming on board in the next 10 years. That's the scope that is happening in that part of the world. Coming to the other one that's going to shape the landscape of the research is about the silver generation, what we call basically people with an age above 60 years. And that number is going to be more than 1 billion people in Asia alone, and obviously that would have enormous impact on the way the economies of that part of the world. And obviously the national governments would be asking some of the solutions that science can provide. So here are the reasons why regenerative medicine is likely to have a lot more interesting reasons. One should focus: aging population, longer lifespan. Not long ago, people were only living up to 40 years, but now the average lifespan has gone up to close to 70 or 80 in certain countries. And then chronic diseases are still there. There is a rising demand for advanced medical solutions. This is what is going on. All those things would lead to more need for regenerative medicine. So I have convinced you why we chose those 3 platforms as our target for applying these building blocks of nature, which is basically nanofibers: water, energy, and aging. So nanofibers, nothing new. These fiber structures are there everywhere. In fact, all the wood panels you are seeing, it has a cellulosic fibers, and so is the bone. All our human tissues in our body has these particular structures. This is a slide from my friend Rob Ritchie from Berkeley. And here is the bone, and you see actually collagen fibers. These are the fibers that provide the certain degree of rigidity, stiffness, as well as toughness to our bones. That's why we are able to jump, we are able to twist and turn, and we are able to chew as well. And here is those who are a lot more interested how exactly this mechanism works. Basically, these fibers are very nicely arranged, and it has a combination of organic and inorganic phases, and these are very structurally arranged, and one could call biomimetic. Essentially, they provide a certain degree of crack bridging, also providing toughness. There's a lot more details the way these fiber structures are arranged in our human tissues. And I'll show you in my work how we actually biomimic this particular structure by using our process, and we produce structures very similar to the natural bone. And of course, these are the spiders. They can walk on the water. Of course, we can't walk on the water, but they can. That's primarily because one of the reasons is they have these very fibrous structures in their legs. And similarly, the geckos, beetles, these things can walk and crawl on the vertical surfaces as well as glass surfaces. Again, reasons are attributed to this kind of unique fibrous one-dimensional structures, a very sub-micron range that are present in some of these creatures that provide that unique ability. And silk fibers, you know that. This was, of course, China was the pioneer. And since then, last 2,000 years, many people use silk. And silk is known for very high quality properties as well as strength. And similarly, the spider silk, which is also quite unique in terms of the toughness. And there are many research groups trying to synthesize the same process to produce such a high quality fiber systems. And if you notice, these are the fibers, nanotubes, nanowires, nanobelts. Most of the work in a nanotechnology. In fact, today I received a paper from Tel Aviv University Vice President Ehud Gajit. He has been producing these nanofiber structures from peptides from the bottom-up process. What I'm talking about is a top-down process of producing nanofibers, much more simpler, reproducible, and can be done in large quantities and on the industrial scale. So that is the process, basically electrospinning, and this is the process how it is done. You basically have a polymer solution. It could be melt solution, and you apply very high voltage and a very low amperage, and that provides certain dynamics into the polymer solution system. Essentially, that provides a very fibrous structure like that. So most of the theories for this process are somewhat known. The basic process is known. There's a lot more work is going on in terms of optimizing the process. Now, if you take that process and you play with it, here is the ways you can actually play with it. You can produce unidirectional fibers. You can crisscross them. You could actually place them at certain angles, and you can pattern them. You could also, of course, that's a machine which came out of my lab, which is my former Japanese student. He's now selling this machine in Japan. And so this is a commercial process now to produce. So you could produce solid fibers, you could produce porous fibers, you could produce core shell fibers. You align them, you can layer them, you can bundle them, or you can make hollow fibers. It basically provides you the flexibility that you could do, and then you could deal with a natural material system or a synthetic systems or a combination of those two. And by further controlling the spatial control of the process, by using electromagnetic systems, you could actually control the spot size, and you can see this is less than 5 millimeter spot size. This is being used to produce next generation dental implants. So my collaborator in the Faculty of Dentistry, they're using this system to improve the quality of the adhesion between the dental implant and the host bone tissue. And of course, you can also play with it further. You can actually start writing in a specific way these fibers. It's pretty early stage, but there is also a direction that is feasible. Now, coming to water itself, as I said, water is a serious issue. There's plenty of water actually. The problem is most of the water is in the sea. As you can see, for Israel, I don't have to say, you've got plenty of ocean there. There is so much of water out there. And the main problem is the fresh water or the groundwater, which is limited. And so that's a saline water. Mostly people use desalination systems. If it is fresh water, you use like varieties of filtration systems. Here is what it looks like. Either some of the surface water, you use basically the combination of microfiltration, ultrafiltration, and nanofiltration. And if you have to deal with seawater, you use reverse osmosis as well. And here are the various things that are removed from the water, essentially leading to the drinkable water. And here are those things. I just show you how we can use our nanofibers. Here is an example. In a microfiltration, this is a membrane which is a red color made from our electrospun nanofibers, and that's the millipore, which is a commercial membrane, and for the same given pressure, it has much higher flux. So that means you have a lower energy consumption. And this is a proven, and right now it is a commercial operation in Japan. It's a company from Czech. It has commercialized based on our concepts, and it is a real process now. And then you could play with the surface of these fibers. You can modify them, tailor this porous structure within the surface layer, and you could use them as ultrafiltration. In this case, we have managed to reject about 90% of the humic acid at a 0.25 psi, as opposed to the commercial ones, which is about 30 psi, would have a rejection of 35%. And the other one, you could further use interfacial polymerization of these fiber structures. You can control the surface, and you essentially make a nanofiltration structures. Here is the nanofiltration membrane of a polyamide material, and that is magnesium sulfate, and test pressure, and that's a rejection level, and that's flux. And these are all commercially available systems. And if you notice, it's 5 times energy efficient compared to other systems. And right now we are trying to further develop this particular system using the same concept. Okay, hopefully one day we will solve the energy problem. Not yet, but I think that's where we want to go. Now coming to the energy, we have a lot more similarities, Singapore and Israel. You can see here, we don't have no oil, no gas, no coal, no biomass, no wind, no hydro, no tidal, no geothermal. Essentially, we have no energy source at all. So what you are left with, options, energy efficiency, solar energy, or waste energy. Basically, those are the only things that are possible for Singapore. And here is the Singapore map, and that's Malaysia. Indonesia is on the back here, on the bottom. And as you notice, the distances are not that large, so obviously nuclear energy would be a challenge for us to convince our neighbors. But we cannot deploy in Singapore either, because it's a highly urban center, 5 million people living 70 kilometers by 70 kilometers, such a small space. So obviously there is a serious issue. So we are looking at solar energy, but it turns out that may not be the ideal solution, but that's something we should pursue. So here is the sun belt of the world, and that's where this is the tiny dot here. We actually don't see it on the map. That's Singapore. And in terms of the technologies out there, the solar cells, basically the single crystalline silicon solar cells, which is most widely used, and then organic solar cells and dye-sensitized solar cells. And how these are the working principles. The reason for using these one-dimensional nanostructures in solar cells, especially the organic solar cells or dye-sensitized solar cell, these are the two reasons. One is because of this structure, unidirectional structures, we believe the space charge free region is a lot more evident in a fiber structure compared to the nanoparticle. So obviously that would give you much longer diffusion times for the electrons to go. Similarly, because of the one-dimensional nature of the structure, these nanorods would have a better way to tunnel these electric charges through the fiber to the electrodes. So these are the two reasons why we believe that's feasible. And of course, there are other processes which you can explain. Yeah. I'll just show you some of the results. For example, when you reduce the size of the nanofiber, you could reduce it to 50 nanometers, or you can also go as small as 30 nanometers. Essentially, by heat treatment processes, you can control the crystallinity within the fiber, and also you can optimize diffusion constants. And here is actually what we have done. Here is a solar cell which is made from the electrospinning, and I just show you some of the results. Yep. Okay, here is the results. So here are these are the nanorods, nanowires, nanofibers. Basically, we define it based on the aspect ratio, and these are the photoexciton densities and the diffusion coefficient compared to nanorods, nanowires, which is basically have a much higher aspect ratio. It gives you much better diffusion coefficient. This is 10 to the power minus 5 and 10 to the power minus 4. That's an advantage by itself. And then, of course, you can do the doping of these fibers, titanium fibers, and then you could actually improve the diffusion coefficients. And here are the examples of the performance of the solar cells, which we made about 5 to 7%. That are the efficiency. And then you could also apply the same thing in hybrid solar cell systems, and these are the results. But the key where we are heading now is combining concepts of dye-sensitized solar cells as well as organic solar cells, and make a photovoltaic fiber. Basically, that's the fiber that is electrospun. But within that fiber, you actually have the electrospun TiO2 nanorods, on which you actually have the dye molecules. So the whole thing is a photovoltaic fiber, and that forms a fabric. So it's essentially a new device structure we are heading towards, and we hope one day the fiber cloth would be a photovoltaic system. And obviously that's how we are beginning to do our experiments. And these are actually the initial results, where you have the TiO2 nanorods coated with the N3 dye, which is one of the ruthenium dye. And these are the examples how TEM examples of these fibers. And you can make them with the different electrolytes, P3HT system, as well as lithium iodide systems. And what I wanted to show you is the first proof of concept. That's the dark current, that's the light current. And you notice that there is an improvement. So if you look at the efficiencies are not very high at this point, but it proves the point such a concept would work. And now it's a question of optimizing this particular approach. And we have the issues in terms of recombination, charge collection issues, as well as the dyes that are issues as well. So we are in the process of optimizing these. So I was just listening to a session before where they were talking about the lithium-ion batteries, and we have done little work. Here is the result. TiO2 anode materials. These are the nanoparticles. These are the electrospun nanofibers. They would provide a much better stable cycling ability than the nanoparticles. Here is the result. We have done up to 50 cycles. So there seems to be some hope in terms of new anode materials for lithium-ion batteries using electrospinning technique. And of course, you could produce a whole range of materials, PZT materials, zinc titanates, niobium oxides, using the same process. And I would go now quickly to the regenerative medicine. I'm switching to the next topic. This is a new topic which has been around only about 10 years. And globally, if you notice, right now the market value of the regenerative medicine is about $2.5 billion, and it is growing substantially. And that's the breakup in terms of the breakdown, bioactive bone grafts, and other skin material systems. And these are the busy slides I won't, but I just take you straight to the results so that we can focus on what you wanted to know. Okay. So here is the material which is made by electrospinning as well as co-precipitation of hydroxyapatite, and you are actually producing a bone analog material very similar to the bone, and here is an example of that material. And then if you implant that in animal studies, and they seems to regenerate quite well. So we have now done the second batch of the implanting, and is also being tested in European countries as well. So this is the test showing us very positive results. Now the other strategy is use these nanofibers to isolate stem cells from the bone marrow. That's also very necessary. And here are some of the results. These are the mesenchymal stem cells from bone marrow, and these are the cover slip, and these are the nanofibers. If you notice, within 30 minutes, you could actually capture close to 50% of the stem cells that are available are present in the bone marrow using these nanofiber scaffolds. And here we are using collagen system. And of course, you further optimize it, you could get a much higher levels of retention of the bone marrow, almost close to 80%. And then you can further enhance this one by optimizing the surface of the collagen nanofibers with certain protein molecules, and you actually further get to the very high levels of retention of the stem cells. The whole idea is you have a nanofiber scaffolds which are very specially suited to absorb the mesenchymal stem cells from the bone marrow so that you can use that for treating the patients in terms of the bone or other areas. And here is an example where we are also using this system to coat the stents. And here is if it works, and you actually see that's a stent coated with nanofibers, and of course those nanofibers could be drug loaded. And right now we are on the animal studies in stage 1. Similarly, the nerve conduits where you could use for the peripheral nerve regeneration. These are the autografts. That's normally you take it from a vein from one location and apply it to another location. This is the commercial ones. These are nanofiber conduits which we made in the laboratory, and you look at the sensory activity of the rats, they behave much better. So there is a huge potential in using these conduits for guiding the axons to grow in a specific direction, and now there's work coming up in Australia to use the same concepts for the central nervous system as well. And the last wanted to show you, in terms of skin regeneration, here is the control. That's nanofibers, and nanofiber scaffolds with a large number of cells, and it's a day 0 and day 10, and you actually see that the regenerative ability of these particular nanofiber scaffold systems. Right now, Vietnam, it is going on a human trials, and probably next time I'll be able to show results on the human trials. So in Singapore, we are done up to animal studies too, but in Vietnam, they're now doing the human trials. The last one, which we are now collaborating with Technion, is a topic called regeneration of myocardial infarction. Here is the infarcted heart. Idea is to develop these particular nanofiber scaffold patches to treat the patients with myocardial infarction. So this is a large program we're now doing with Technion. I just want to convince those who are not convinced. It's an interesting area. About 800 papers are being published in electrospinning right now, and it's a relatively young field. About 7 years ago, not that many people were active, but it's growing very well. And that's a citation trend. This is how the activity trend in various countries. And this is just not a laboratory process. You actually see a number of companies around the world actively involved in electrospinning process. And these are the commercial machines that are available out there already. So I just want to show you this slide, and I'll finish my presentation today. This was done by my students. They figured out you don't need to do such a complex projects. Let's do something simple. So what you have is a petri dish. There's a beautiful lady out there, and this side is uncoated, and this side is basically coated with nanofibers. And because this nanofibers has a wicking effect, it basically takes away the water and then it provides a clear vision. And so they are thinking now to use it for this kind of application. This is the rear view mirror, and this is a coated rear view mirror, and obviously you can see the difference. So with that, I just want to say, it's a field rapidly evolving. I would imagine the breakthroughs can come from any part of the world. Thanks for your attention.
Thank you, Professor Ramakrishna, for a very comprehensive analysis of many important problems for mankind. And I think we have plenty of time for questions and comments. Please. Yes, Anthony.
Okay. There are a few. when the first process, maybe I give the detail. The first patent was filed about 100 years ago, and I think it's a UK citizen, but filed in the United States about 100 years ago. Nothing really happened for 50 to 60 years. Then the Russians were started using during the Second World War for the chemical warfare protection as masks and things. And then it resurfaced in United States. A company called Donaldson started using this for agricultural purposes, where they're using this as a filter for the agricultural tractors and those kind of vehicles. If you look at what they have done, essentially they use this technique and just sprayed the fibers, which are basically submicron in nature. Since then, what has improved is ability to understand what exactly happening, how the fiber is produced from a polymer solution to such a very fine size. Compared to the conventional process, you need to draw it to many times, whereas you don't actually do anything. So the process of evolution of this Taylor cone, further reduction into the very fine dimensions, that has been clearly understood. The innovations are how do you produce, let's say, a specific orientation or a specific diameter. These are where the advancements were made. And more advancements came on actually the material systems that are used, and thus this material systems would now provide better properties if you have this fiber structure. So this is, for example, PZT material. The same material in the film form would have a certain properties. If that same thing is produced now with a nanofiber structure, it would have a different degree of the piezoelectric effect that has been reported. So the unique properties in terms of the piezoelectricity, the unique properties now we have reported in terms of the diffusion coefficients for the electron, those are basically the structures that are feasible in this one. Third one is in a regenerative medicine. I still remember about 15 years ago when I went to Johns Hopkins, I went with my fibers. Most people were using hydrogels and phase-separated scaffold systems. They thought that's good enough. But I can tell you now, almost I would say 50% of the United States tissue engineering groups, they definitely have electrospinning as a part of way to produce scaffolds, because they just found the fibers need three-dimensional structures, and you also need a way to send the nutrients and oxygen and other elements as you are doing the tissue culture. So that's, I would think, considered as a breakthrough. And is there a real breakthrough in terms of the blockbuster application, in terms of the tissue regeneration? Not yet. Yeah. Yeah.
Please, Professor Lifshitz.
If I understand correctly,
Yeah.
the fibers that you are talking about are polymer fibers, essentially.
Yeah.
And of course, their mechanical properties are limited. Can you comment on the status, on the efforts of trying to increase the mechanical strength of these fibers by, let's say, as an example, introduction of carbon nanotubes or diamond crystallites, or what is done in that direction?
Yeah, good question. In that, there are two things. Majority of the work in the last 10 years has been focused on polymers, but now you are beginning to see a trend of moving towards metal oxides, primarily because of the electronics and optical, that kind of applications. And in terms of the polymer systems, the work that is done is there are only 3 to 5 groups that are focusing on mechanical aspects, and they have focused on looking at the crystallinity aspect. How does the crystalline structure of the polymer from a solution to the fibrous structure when you electrospin, what is the change in the morphological aspects, and how that actually improves the mechanical properties, in this case mainly the tensile strength. And they use the AFM, atomic force microscope, as the way to characterize these systems. And there is some reports, especially from Drexel University and a few others, started introducing carbon nanotubes inside. And recently they're putting inside fullerenes, as well as there's a newer structures that are being put there. But again, while they're exploring the mechanical aspects, they're also branching out to functional films, where they're looking at supercapacitor systems. They're looking this as a material for the batteries as a separator. So between some of the battery systems, electrochemical systems, they are using this again. So very few groups completely focusing on improving the mechanical aspects. Many others are looking at a multiple functionality. Is there a scope for doing more work in terms of improving the properties? I would think so. There are people now working on carbonizing this one, producing just carbon fibers out of that. And then how do you improve the properties of those fibers as well? And then it depends exactly where the application is. For example, in water filtration, eventually the strength comes into a picture because you're not pushing the water, a small quantity of water. This is a large volumes of water being pushed through the membrane. So the mechanical integrity, a longer period, able to survive the backflush, all these things have to be worked out, and mechanical aspects would need to come in. Maybe why they did not focus is it is somewhat difficult because you need a special instrumentation to handle this, such a fine fibers, and the loads involved are not that high. But so that's probably why most people did not focus. But that's something one should focus as well. Yeah.
Other questions?
Can you elaborate a little bit more on the solar cell application, and in particular, what is the architecture? Are these fibers somehow or other erect on the electrode, or they're just laying randomly?
We all hope we can erect them in a vertical or one other direction, but right now most of them are random. And they're roughly in the thickness of about several microns. So we build certain thickness. And one of the key problem there is it delaminates. So most people are focusing on how to avoid delamination. So the later approach which I just said, we're now not focusing on just how do you put these vertical fibers on a FTO glass. The question is, can you actually make a completely photovoltaic fiber by electrospinning? And that's probably gets it more interesting. And that's probably where there is a scope and edge for such a process. Otherwise, you are competing with other processes. So my own view is making it completely photovoltaic fiber using this process would have an edge. Only one company that is doing in the fiber structure, that is Konarka in the United States, and of course the EPFL is involved. But their process is not electrospinning, they do the multiple coating. I do not believe that would be a system that would provide what we call solar fabrics. That would be just thick rods. That's what they can come up with. If they had to go towards the really truly photovoltaic fabric system, they have to figure out how to produce, how do you put all these systems inside? You need to have both anode, cathode, electrolyte, dyes as well inside. And eventually that has to work as a complete system in the fiber form. And the second issue is how do you actually tap the electrons out? So these are the serious challenges. But whoever can do it, even with 1% efficiency, I think it's already done. Because you do not need, this is for the low energy applications. So I think even if anybody can come up to 1% efficiency, I think they already have a good certain scope in the market. That's my belief.
Thank you. And I think I'm not seeing more people would like to ask questions, and we are a little bit rest on time. I think we have to thank speaker again for a very nice presentation.
Thank you.
And by this, the scientific part of the conference is finished. I guess organizers are here and are ready to close the conference and to provide some remarks. Noam is here, or Ilan Goldfarb, somebody from organizers. You. Okay.
Well, actually, we're waiting for Elon and Noam to finish, but they should be appearing momentarily. In fact, I see Elon now.